non-singular varieties via tangent space, right? So tangent space is at a point is just the essentially order 1 approximation of the variety around that point. So it's the zeros of ix1. So how does ix1 change according to p? So here we assume p to be the origin. So we have made sure that the variety passes through the origin, and around the origin you just take the linear part. Okay, so ix1 is generated by linear forms, fi1s. If it was a different point, then you have to shift the variety by that so that it passes through, so that you basically, instead of studying an arbitrary point, you always study the origin. You can also define this without shifting to the origin, but then you have to suitably modify the definition. It becomes more complicated in the notation. So here we are defining tangent space at the origin basically. And then we showed that the tangent space, which is a linear space also, so its rank over the base field and the rank of the first order partial derivatives of these polynomial generators, that sums up to the ambient space rank, which is n. And we also study functions on the tangent space, which is called the dual. So that dual is txp wedge. So this will be the linear, all the linear forms modulo ix1. Okay, so this is the functions defined on the tangent space, and we showed that it's actually related to the germs around P, which is MP mod MP square. So rank of all these three things in particular is equal. Any questions till now? Okay. Yes, so we have shown these rank results, and then we come to the important question of how to handle singularities. So we took an example, this real picture, which is x2 square minus x1 cube. So we took this curve, the point of singularity is 0 because there the tangent space is the whole space actually. You can show that the rank is 2, which means, it should have been rank 1, for example, at some other point P, tangent space is simply that red line, but at the origin it's actually both the axes, so it's the whole space. So how do you handle that? So we'll now focus on that question, and ultimately we'll show that any variety, any curve can be transformed in a way so that it become non-singular. So for example, here what you could have done is draw this picture instead, which is the picture of y square equal to x1. Yeah, so what we did in this case is we use the transformation x2 over x1 equal to y. So that's the curve here. This is y square equal to x1 curve. Okay, and y is related to the previous coordinates as this. Y is x2 by x1. So if you do that transformation, so this is a rational function transformation. If you do that, then you basically you are magically transforming your older picture to this diagram where you see that everywhere points are smooth. Tangent spaces are just lines. So here also now you have this line. Okay, so at every point you have now smoothness. And we had already checked before that these two curves are birational. X2 square equal to x1 cube and y square equal to x1. They are birational. So we have shown, at least in this case, that one point of singularity can be removed, can be replaced by a smooth point in a birational curve. And we want to do this in general. We want to do this with multiple points of singularity. So for that we have to develop some significant amount of algebra which is motivated from other areas in math, in particular algebraic number theory motivates this. So it is called DVR, discrete valuation ring. So what we want is locally this ring of germs, we want that to be a DVR. We will show how it relates to smoothness or non-singularity. So yeah, so the question you should ask here is how to get smooth x tilde birational to x. Okay, so this is called resolving singularity by blowing up. So how to blow up a variety around a point so that the singularity is gone. Okay, the point becomes smooth. So the process is called blowing up. Because a point, so a singular point which was originally, let's say, x1 comma x2 coordinates is being mapped to x1 comma y x1 comma y. So in particular 0 0 was mapped to 0 0 1. Okay, I mean I think it should be thought of as a projective point. So it's x1 quotient phi x1 quotient phi, because what we did was we took ratio of x2 and x1. Okay, and that we called y. So we introduced this. Of course, that ratio locally was not defined because x1 and x2 were 0 and 0. So 0 over 0 wasn't defined. So basically we are introducing something which was previously undefined. In that sense, we are blowing up. Okay, we are adding some new things in that neighborhood. Which is why the transformation of the two diagrams is not that smooth. I mean, it is not clear how this picture became this, right? How did the curvature change so that the origin becomes a smooth point? So it's a complicated operation. But the key thing is that you want ultimately the function fields to be isomorphic, right? You don't want to do it. You don't want to go to an arbitrary curve, but you want to go to a curve which is tightly related at the level of functions. That is what this achieves. So instead of giving the just the theorem statement, I want to show you the properties one by one, the things that we want to preserve. So, the properties we want in this process are, so the first property is that this coordinate ring that you get, the new coordinate ring in that example, the germs, the ring of germs which you get is Ax tilde, the coordinate ring localized by the prime, which in fact by the maximal ideal MP, which is x1 comma y. So this is a local domain. That is clear because it is localized by a prime. It's a local domain which was also true for Ax localized at MP. The new thing which has happened is its maximal ideal is principal. It has unique maximal ideal. Now principal.
Here x tilde is x1 y.
X tilde is the second picture, y square equal to x1. The one which is birational to x and no point of singularity. So, in the special thing about this is that now the germs are, I mean, it remains a unique maximal ideal, but actually it becomes principal. It has a single generator. So, why is that? That's easy to check. So, it is the ideal generated by x1 y, right? X1 we have set to y square, which is generated by y. So, in Ax tilde, this is actually a principal ideal, which then gives you the unique maximal ideal, which is principal. While previously what was happening was you had x1, x2, but this isn't a principal ideal. You can show that there is no common generator, is non-principal in Ax. Okay, so the ring of germs or basically these germs which vanish at the point, that ideal was non-principal before, but now the germs that vanish, it's a maximal ideal which is principal. And this generator y is of course a very special element. Okay, so because this is exactly the new thing which we have introduced. So we'll call it uniformizer, and that motivates this general definition in algebra. So a ring R is called DVR discrete valuation ring. If it is local, it's a domain, which means it's an integral domain, so it has no zero, it has it has no zero divisors. Yeah, local is by definition unique maximal ideal. Is the domain thing correct for Ax localized? Yeah, okay, that is correct because of the variety property, modulo prime ideal. Yeah, if it is a local domain with the unique maximal ideal principal. So this is the key condition here. Everything else is old. The key condition is that in DVR you want the maximal ideal to be unique and principal, and the whole ring to be a domain. Yeah, so you have already seen, and I already gave an example. Yeah, you already saw an example of DVR, and you also saw an example of a ring which is not a DVR. Another example of such a ring is, maybe I can just list here. So this ring that we had, K x1y mod localized at y x1y, this is a DVR, while the older one localized at x1 x2 is a non-DVR. What about the ring of integers? So the ring of integers is a domain. Its maximal ideals are always principal, right? But the problem happens somewhere else, which is it has many maximal ideals. There is no unique one. So it's not local. So Z is not local, though every max ideal is principal. So I mean Z is non-DVR, right? But it comes very close, because you can see that its field of fractions is rationals. Z is a domain. Maximal ideals are principal. But for DVR we need a unique one. Any questions about the definition or examples? Yeah, so this is DVR. Now the other property I want to focus on here is this word valuation. So what is the meaning of valuation here in this definition? So that's property 2. So if R is a DVR, so let's look at the tower. So base field K, then you have unique maximal ideal, then you have the DVR, and you have its field of fractions, which is K, big K. Okay, and this is a DVR. Where K is the field of fractions. I think we wrote it like small k of R. So K is the field of fractions and M is the unique maximal ideal. Okay, so whenever I draw this, I will always mean that R is a DVR, big K is the field of fractions of R, M is the unique maximal ideal, and small k is the residue field. So small k is R mod M. Maybe we write that also. That's the residue field. Yeah, so DVR actually imposes some very nice functions and properties on big K. So what it gives you is, then there exists a way to map every non-zero element to integer. That satisfies metric like properties. Okay, so for DVR there is a way to define metric, and this V, small v, will be called valuation. So what is this metric like property? So let's look at the definition of that.
So one question, why A is inside M?
Why K, small k? Yeah, I don't know, that's a mistake. I have to use a different hour. Yeah, it should be outside. It's in fact an ideal. Yep, is that fine? Okay. So we call it a valuation, a discrete valuation of a field big K is a map V such that for all elements xy, so V of x times y should satisfy something like degree. So okay, so degree of product, degree of product of two polynomials is the sum of the degrees. So that kind of a thing. And what about the sum? Yeah, so since big K is a field, in particular it's a ring, so we want the valuation to behave nicely with addition and multiplication. So with multiplication it will be this exact property, it will be the sum of the factors. For addition it will not be exact, it will be what? Should be at least both of these, well, the smaller one. So minimum of the valuation of x and y. Okay. So what is the intuition for this? So it's kind of opposite of how the degree behaves. That if you add two polynomials, then the degree can only reduce, it cannot increase. But here we are saying if you add two polynomials or two elements in the field, then the valuation cannot decrease, it can only increase. It's the opposite of degree. So valuation of y times y, yeah, I should not confuse this y. Yeah, maybe I just change this. because in the previous example we had the uniformizer y. Okay, so now in the previous example, in the example above, our ring R is kxy x1y mod y square minus x1 localized at x1y. So I have to show you why this valuation map exists, right? So before that we have to understand what are the elements of this ring R. How do they look like? So any element alpha in K, the function field of this ring can be written as so it will be a ratio of two polynomials. Now each polynomial will be bivariate in x1 and y. x1 can have arbitrary degree, but in y we'll only use either 1 or y, right? Because when you get to y square, you can replace y square by x1. So every element looks like this. It looks like a polynomial in x1, y times a polynomial in x1 divided by a polynomial in x1. Okay, so this is how any fraction in the function field of this R, fraction field of this R can be written as, okay, it has a 1 part and it has a y part. And these fractions a over c and b over c are univariate in x1. Is that clear?
Why the denominator is always cx1?
Yeah, because if you had a prime plus y b prime,
Then it lies in xy.
no, then you can multiply it by the conjugate, like a prime minus y b prime.
Okay, okay. I see.
That's the trick we are using. This is equal to a square minus y square b square, and y square is x1. That's the identity. Yeah, so denominator can be made univariate at the cost of numerator being bivariate with 1 and y. So yeah, so what is the valuation of this? So we'll define valuation via the uniformizer y. That's the idea. So basically express alpha as the highest power of y that you can find, let's say y to the e, multiplied by alpha prime, where alpha prime goes outside the ideal. Okay, since the maximal ideal M is generated by y, what we are essentially saying is that you just divide by the maximum power of y, and then the remaining thing will not be in the ideal M. Okay, but you are still in the ring R, in the DVR. So this E you should call valuation. Of course, E is integral. Okay, because remember that alpha is an element in the field, so you can also have 1 over phi. So in the case of 1 over y, you have to remove y raised to minus 1, and then you will be left with a element outside the DVR. So the valuation in that case will be minus 1. So valuation is integral, negative, 0 or positive, integers. So with that understanding, valuation of x1 is what? So you have to see how many y's divide x1, right? X1 is y square, so valuation is 2. Okay, so valuation of x1 is 2, and what is valuation of x2? Well, x2 is not a variable written here, but the map was x2 equal to y times x1. We are using that definition. So what is valuation of y times x1? That is, yeah, you can check that it's actually comes out to be 1 plus 2, 3. Okay, because y x1, or you can simply just replace x1 by phi square. So it's the same as valuation of y cube, which is 3.
No, how can it be 3?
Yeah, so let's not use this formula because I have not proved this. This you have to verify. Well, okay, no, when I define, the way I have defined it, you can already check that valuation of alpha beta. So here axioms are satisfied. This can be checked. The axioms being, once I have defined it like that, you can see that alpha multiplied by beta, whatever is En, E1 and E2, you will just sum it up. So valuation for product will be sum, and valuation of sum alpha plus beta, you can check that it will be at least the minimum. Okay, so the valuation axioms here are actually immediately satisfied as soon as I define it like this via division of y. Yeah, and then do the example either way, but I can also do it directly. So this is valuation of y x1 and valuation of, which is y cube, because x1 is y square, so you get 3. Fine. Okay, and what is valuation of 1 plus x1? So here you can check that y cannot divide it. I mean, you can just check that 1 plus x1 is in the ring, R. And so E is 0, valuation is 0. Sorry, in the ring, okay, I have to give the reason here. Since 1 plus x1 is in the ring minus M, that's the reason. Or to put it simply, it's a unit in the ring R. Okay, so these units, the way we have defined it, y is the key non-unit element, and units cannot be divisible by y. So those are, units are all valuation 0. And what can you say about the elements whose valuation is positive? They clearly are the non-units, right? Because they, all the positive valuation elements, they are actually in the max ideal M. because they're all multiples of y, and y is the generator of m. Okay, I'll write that later. One more example. So what is valuation of 1 over x1? 1 over x1 is a valid element in the function field, so you can talk about its valuation, and its valuation will be the opposite of valuation of x1, so minus 2, right? Okay, so is the definition and the examples clear? Right, so what we have shown, let's collect it in a proposition. If R is dVr, then there exists a valuation V. Further, you can see that the elements in K star yeah, maybe I should define valuation of 0 also somewhere. Let me put it here. What do you want valuation of 0 to be? So valuation of 0, by that definition, you want basically phi to the e to divide 0. That's possible infinitely many times. So let's just call it infinity. Okay, so that our theorems and axioms are correct. So for example, if you multiply alpha with 0, right, so valuation of alpha times 0 is infinity, which is fine because valuation of alpha plus valuation of 0 is also infinity, no matter what alpha is. So yeah, no negative number can reduce infinity except minus infinity, but we don't have minus infinity anywhere. And second axiom is also true. So yeah, let's take valuation of 0 to be infinity by definition. That will simplify some confusion in the statement. So yeah, so now I can say those alphas in the function field, in the fraction field, with valuation non-negative, it's what? What is this set? Yeah, so m actually is positive, and if you also include the zeros, you are including the units in R, so you get the whole of R, right? So if you focus only on positives, sorry, then you get what? This is m, and what is, if you focus on zeros, this is what? So this is obviously R minus m, and which is the units in R, so R star. Fine. So this is what we have shown, right? Because from dVr we get that m is principal, so you get a uniformizer. With respect to that, you can define the valuation as we did in the example, and from that everything else follows. So dVr implies that m is generated by something, let's call it y, or let's call it u. Uniformizer of R in K. Okay, it's in this context. So u is an element in K, and it generates the maximal ideal of R. And with respect to this, you can define the V. Alpha prime in R minus M. That defines V of alpha. Okay, and you can check that all the properties are satisfied as above. Oh, I could have written one more. What about the negative ones? Where is that? What is this? It's obviously it's outside R and inside K, right? So it's K minus R. Yeah. So you have the whole range. You can start with things outside R that will have negative valuation. Then when you come inside R, you are into non-negative, and when you come inside M, then you are positive. Okay, that so it nicely organizes the things if you have a DVR. Yeah, there are other properties. We will not prove everything. Okay, one thing that I'll need. Okay, let's do it later. So prove that if a field K over small k has, or let's just say K, has a valuation then there exists a local domain R of I think transcendence degree 1. How do you show this? So now you are not given a DVR, you are directly, somebody gives you a valuation. R wasn't given to you. R you have to find. So what you can show is that from the definition of valuation and these properties, right, if you are given K and you are given V, then from that you can recover R. And you can recover M, and but the thing is that how do you, I mean, you want to prove that actually M is the unique maximal ideal. How do you recover that information? So we are saying that that also is true. How do you show it? So V defines R and M, but how do you show that M is unique?
Because outside this ideal, everything is unique.
Exactly, yeah. Implies that R minus M is unit. So which means that R is local. How do you get this transcendence degree 1 information?
Principal
Yeah, so do you get principal ideal? I'm not sure about that. I don't think you can deduce that there
If
is a.
you are given a valuation, that will be respect to some single element, right?
No, valuation just exists. It just exists.
It can be based on the maximal ideal also, not based on a single element.
Yeah, I mean, you don't know what it is based on. It's just a map which is given satisfying the axioms. So from that you have to deduce that transcendence degree of R is 1. I mean, so you get very close to this uniformizer. There is a single generator that you have to show. Yeah, so this you have to finish as an exercise.
So transcendence degree 1 will necessarily imply that the maximal ideal is principal.
No, it will not imply that. Well, we have seen examples, right? In the singular case,
Okay.
we just saw an example.
Yeah.
I mean, for curves, it's very easy to construct non-DVRs because you can just take singular points and the germs. That's all non-DVR.
Then you have to find the generator of the maximal ideals also to claim something like that.
Yeah.
Sir, this is not clear to RS local. Like V is some random valuation.
Yes.
So we define R to be all the points where V of alpha is greater than 0.
Correct.
And M is V of alpha greater than strictly greater than 0. There.
Yes.
But this valuation is not the same as like any random valuation.
Yeah, it just satisfies the
Valuation criteria.
valuation axiom.
We can show that M is an ideal. How you should for any V in R and SM, you just know that the valuation is greater than 0. How do you show this unit?
If it was not a unit, alpha, so then alpha times beta, there is a beta such that the product is 0. And that's it. So now you see, you get that valuation of alpha plus valuation of beta is infinity. So infinity means that one of these has to be infinity. So yeah. So there are these tricks you can use. It's a good exercise. So let me proceed so we go to the third property. We have seen two properties, right? What's the third property? So that will be another a new buzzword which we'll study. So first was DVR, second was valuation, and third is integrally closed. So DVR R is integrally closed in its field K. So integrally closed means that I mean, it's something just short of algebraic closure. So that we have to define it. So R is called this integrally closed if any polynomial fx so we actually are looking at a monic polynomial. So first coefficient is 1, then you have in over Rx. So AIs are in R. So if you take a polynomial with coefficients from R and the leading coefficient 1, so monic polynomial, if it happens to have a root in the field K, if a monic polynomial fx with root alpha in K implies that alpha is in fact R. Okay. So if any monic you take any monic polynomial, you take any root of it in the field K, then that root in fact is in R. Okay, when this happens, we say that your ring is integrally closed. Okay, the only difference between this and algebraic closure is that in algebraic closure you will take an arbitrary fx, but here you consider a monic fx. So up to monic, this is all the roots are already present in the ring. What is the example of such a ring? So there are very simple examples. The first one being the ring of integers. That is integrally closed. So all this is actually motivated from there, from algebraic number theory. So Z is integrally closed in rationals. Why? So say alpha square plus 2 alpha plus 3 is equal to 0 and alpha is rational. Can you show that alpha is in fact integral? Let's think of alpha as a over b, ab integers. So this means that a square plus 2ab plus 3b square is equal to 0, right? Now what? Now this means that b divides a. Which implies that alpha is actually integral itself, right? So you can use these tricks. This is called Gauss lemma. It says that if for a monic polynomial you have a rational root, then it's actually an integral root. It's a very old result. We use it all the time, right? So this gives you the idea why the ring of integers is integrally closed. Also, in fact, gives you the idea why we call it integral in the definition, integrally closed. So DVRs have this property. So we'll actually prove all these things in a single proposition, but before that, so to resolve singularity, we should pick the integral closure of the germs in the function field K. So to resolve singularity at P, we should take the integral closure of the germs OXP in Kx. Okay, so the idea is this: because you want to go to a discrete valuation ring, this is what we did in that example. We had the germs OXP, which was not a DVR, so we actually just kept adding elements in the ring from the function field, so that it actually becomes bigger and it becomes a DVR. Once it is a DVR, then we have the correct resolution. Okay, so this is why we call it, another reason why we call it blowing up, because we are actually blowing up the ring also to make it a DVR. And this is exactly the thing, we are going to the integral closure in the field. So yeah, let's collect all these claims that I have made and prove them. So for local domain R, with fraction field K, of transcendence degree over the residue field 1, the following are equivalent. So number 1 is R is a DVR, or K has a valuation, with valuation ring R, and R or R is integrally closed. Okay, these three statements are equivalent. These are the three properties we mentioned, that which we'll want. So let's quickly see a proof of this.
The valuation ring, or with that we mean all those greater than equal to 0.
Correct. Yeah. The tower M contained in R contained in big K. So that R is called valuation ring. It's the elements which have non-negative valuation. Right. So let's first do 2 to 3. If there is a valuation, then this valuation ring is integrally closed. How do you show this? This seems to be the most interesting part here. So let V be the valuation, and yeah, so for integral closure we have to look at a polynomial and a root. So say alpha to the n plus is equal to 0 with ai's in the valuation ring and alpha in the field. Right. So suppose there is a root which is in the field satisfying a monic polynomial A over the ring. So the only thing you have is valuation, so let's apply that. So applying that, you will learn that the valuation of alpha to the n is equal to the valuation of the remaining thing. Which gives you what? So this part, the RHS is now we apply the valuation axiom. So valuation axiom tells you that this is at least the minimum, which is it's at least each of these ai alpha I. And this will tell you that n times valuation of alpha. So this means that n times valuation of alpha is at least Yeah, so valuation of AI is non-negative, so we ignore that, and you get yeah, you get I valuation of alpha, which means that valuation of alpha is non-negative, which means that by definition alpha is in R. Okay, so this proof is totally syntactic. Just from valuation you can get this very powerful thing that the valuation ring is always integrally closed. You didn't do any algebra or geometry here. From here now you want to think one more thing you can learn from here. You learn something about the uniformizer, right? This is yeah, maybe that should be written also. Let alpha be the least value element in M. Yeah, it may not be unique. Let alpha be a least value element in M. I mean, M obviously has infinitely many elements, but their valuations are one or more, right? So if you take the least one, you can show that it's a generator of the ideal. Okay, so as an ideal of R, this least value element will generate. It's not a good choice. Let's use U. Yep. Is it clear? How do you prove this? So you may have two elements U1 and U2 with the same least value. How do you show that they generate each other? You look at the ratio. Maybe we should write it here.
Ratio is a unit, so
Yeah. Sorry, 0. Valuation of U1 divided by U2 is 0, and which means that it's a unit. Right, which means that U1 U2 ideal is the same as U1 ideal on U2 ideal. Each of these actually individually generate whatever you want. Okay, so this is again a powerful thing. Just by the least value element you can find the generator.
So this also gives that image. Then from second property, this thing will follow.
From yes, yeah. So but we are not done, right? So we showed 2 to 3, and we showed 2 to 1. So what remains? 3 to 1 is still, I think, not clear. 3 to 1 we should show. Yeah, from DVR the valuation was immediate. From valuation you have gotten DVR. So 1 and 2 are equivalent actually. And we have gone from 3 to 1. Oh, sorry, we have gone from 2 to 3. So the only thing remaining is 3 to 1. Let's do that. Okay. So this from integral closure, I want to show you that there is a single generator. Consider elements alpha beta in M. So since the transcendence degree of K is 1, we have an annihilator. Some polynomial, maybe a big F. So there is some annihilator which is non-zero polynomial, in which if you substitute alpha beta you get 0. I mean there is an algebraic relationship. So this algebraic relationship I will deduce from here that what it is giving you is alpha raised to some exponent times a1 plus a polynomial f1 is equal to beta to the e2 a2 plus f2, where a1 a2 are non-zero field constants and f1 f2 are in the ideal generated by alpha beta, and e1 e2 are of course can just assume it to be in order natural numbers. Is that clear? I mean whatever is the algebraic relationship, you can rearrange things so that the monomials which are divisible by alpha power, you can collect them in LHS, and the remaining terms are kind of alpha, they are alpha free. Yeah, so they may have beta, then they will be forced to have beta, and you can take out b to the eta 2 e2, and then you have a unit element basically. So a1 plus f1 is a unit and a2 plus f2 is a unit. Okay, that's the relationship. This comes from transcendence degree 1. From here we want to invoke integral closure. So the first observation is, if E1 is 0, then E2 is also 0. Why is that? Yeah, if E1 is 0, then it means that, and E2 was positive, then in particular beta divides LHS, and LHS is a unit. So you get that beta is a unit. You have assumed beta to be in M, right? So it's not a unit. So then yeah, so if E1 is 0, then E2 is 0. In that case, what will happen? Well, which actually cannot happen. Both of them cannot be 0, because which will be saying that the annihilator will not even depend on alpha beta. The relationship has to be there, so one of these has to be positive. So we know that both of them are positive now. So this means that 0 is less than E1 and E1 is less than equal to E2. And from here, so I can then look at, I think, alpha over beta. Yes, let's look at alpha over beta to the E1. So you have this thing remaining. Right, so this means that alpha over beta, which is obviously in the field element, in the big field element, this satisfies, is a root of y to the E1 equal to this thing, right? So alpha over beta, this big field element, is a root of this polynomial, which is a monic polynomial, and it's a polynomial over R. Is that correct? Why is this RHS in R? Well, beta was in R in fact in the maximal ideal, and everything else is a unit. So clearly this is a element in the ring. So you have a monic polynomial with a root in the function in the fraction field, and you have assumed R to be integrally closed. So this means alpha by beta is actually in R. Fine. Since R is integrally closed in K. Okay, so with this I think we are almost done. So this means that if I look at the ideal alpha beta, this is generated by beta, right? Because alpha can be obtained from beta. So basically you take any two elements in R or in the maximal ideal, you only need one generator for that ideal. So by repeating this to all the elements, you get principal. We get M principal. Okay, so we
It should be generated by alpha, right? Because alpha by beta and R implies beta is.
no generated by the denominator. Alpha is beta times an R element.
Okay.
So M is principal, and this means that R is a DVR. So that finishes the proposition. Okay, you have all these equivalences now. You shown 1 and 2 are equivalent, 2 goes to 3 and 3 goes to 1. So everything is equivalent. Is that fine? Okay. So next what we will do, we find all the valuations of this pure field Kx. Okay, we'll do this next time. we'll characterize the valuations of the affine line. Okay, so we'll first characterize the valuations of the line, and then from there we'll characterize the valuations, or we'll get the valuations of any curve. And from there we will define the non-singular curve, which is birational to a arbitrary curve with singularity, which had singularity. Okay, so we'll take I think 1 or 2 lectures for this.